Look around you for a second. Think about a glass of soda just sitting quietly on a table, or even the blood effortlessly pumping through your veins, perfectly regulating your oxygen levels. It all seems so calm, right? So still. But honestly, this stillness is a profound deception. Because just beneath the surface of our quiet, everyday reality lies a chaotic, microscopic battlefield.
To the naked eye, these systems, whether it's that glass of soda or a massive industrial complex synthesizing fertilizers, they look entirely static. They look like they're at rest. But the reality? What you're actually looking at is a high-speed molecular war zone where trillions, literally trillions of molecules are violently colliding every single microsecond. Now consider this idea, because it kind of completely shatters our basic assumptions. What you are witnessing isn't the absence of action. It is a perfectly balanced war. We usually think of chemical reactions as a one-way street, a start and a finish. But most reactions are actually two-way highways. Reactants become products, and products turn right back into reactants. When they do this at the exact same rate, they hit what we call dynamic equilibrium. So here's our battle plan for this explainer to decode all of this. 1. Foundations of the invisible war. 2. Mastering the ice table. 3. Stressing the reaction. 4. Thermodynamics and universal balance. And 5. The 2026 AI revolution. Let's jump right in.
Section 1. Foundations of the Invisible War. The Rules of Engagement.
Okay, we need to clear up a massive misconception right off the bat. Dynamic equilibrium absolutely does not mean you have equal amounts of reactants and products. Not even close. It means you have equal rates of change. The exact speed at which products form is the same speed they break back down into reactants. It is a continuous, perfect standoff. And to measure this standoff, we rely on the law of mass action, which gives us the equilibrium constant Kn. Think of it as a mathematical ratio of products over reactants. But there are strict rules of engagement here. You only include the players whose concentrations can actually change. So gases and aqueous solutions, they make the cut. Pure liquids and pure solids, they are completely excluded from the equation just because their effective concentrations stay pretty much constant during the whole battle. Now, depending on the battlefield itself, we might need slightly different tools. Dealing with solutions, we use Kc, based on molarity and concentration. But if we're looking at a purely gaseous war zone, it's honestly way easier to measure partial pressures, so we use Kp for that. And these aren't just isolated ideas. They're mathematically linked. Kp equals Kc times RT to the power of delta N. Moving to Section 2, Mastering the Ice Table, the Tactical Tools. All right, welcome to your ultimate tactical tool, the ice table. Initial, change, and equilibrium. Imagine we start out with 2.00 molar of hydrogen and iodine gas, an absolutely zero product. That's our initial row. As the battle kicks off, the reactants decrease by some unknown amount. Let's call it negative x. The product side, which has a coefficient of 2, gains positive 2x. That's the change. Add those rows up, and bam! Your equilibrium row hands you the exact algebraic expression you need to solve for that final balanced state. And this illustrates perfectly how we can track a system before it settles down, using the reaction quotient, or Q. Now, the formula for Q is exactly identical to K. The difference: Q is just taking a chaotic snapshot of the exact moment we're in right now, whereas K represents that final peaceful equilibrium. Think of Q as your strategic compass. If Q is less than K, you've got too many reactants, and the system shifts right. If Q is greater than K, it shifts left to chew up those excess products. Section 3. Stressing the reaction. Le Chatelier's principle. Back in 1884, Le Chatelier figured out that if you stress a balanced system, it's going to shift to counteract that stress. Let's rapid fire how we can weaponize this. First, concentration. Add more reactants, and the system violently shifts right to consume them. Second, pressure and volume. If you crush a gas by dropping the volume, the system instantly shifts to the side with fewer total moles of gas, just to relieve that pressure. And third, temperature. Listen closely to this one. Changing the temperature is literally the only factor that permanently changes the actual value of the equilibrium constant K. But before we move on, I have to warn you about a classic trap that gets almost everyone: the inert gas trap. If you inject a totally unreactive, inert gas, like argon, into your container but keep the volume constant, the total pressure goes up, right? But here's the catch. The partial pressures of the actual combatant gases haven't changed at all. So the equilibrium doesn't shift. K is completely unaffected. Don't fall for it.
Now, I really want you to consider the sheer scale of what we're talking about here. 8 billion. By completely mastering Le Chatelier's rules, specifically by tweaking temperature, pressure, and concentration, engineers built the Haber-Bosch process. This single industrial application of chemical equilibrium pumps out the synthetic fertilizer that currently feeds over 8 billion people on Earth. It's a microscopic principle that is quite literally keeping humanity alive.
Section 4. Thermodynamics and universal balance. The deep science. Let's zoom out and see how this builds our fundamental understanding. Every chemical system out there is desperately trying to minimize its Gibbs free energy. When a reaction is highly spontaneous, standard Gibbs free energy is negative and K is massive, meaning products completely dominate. But when a system actually hits dynamic equilibrium, delta G drops to exactly 0. The chemical ball has basically rolled to the absolute bottom of the energy valley. There's zero thermodynamic drive left to push it in either direction. And to tie this thermodynamics directly back to our equilibrium constant, chemists use the Van 't Hoff equation. This is just a beautiful piece of math. It lets us uncover the exact heat, or enthalpy, of a reaction simply by tracking how the K value changes at 2 different temperatures. It is pure mathematical elegance. Finally, Section 5, the 2026 AI Revolution, Automated Laboratories. Okay, first, we need to understand the common ion effect, which deals with solubility equilibrium, or KSP. Imagine a saturated solution, and you drop in a shared ion. Le Chatelier's principle instantly kicks in and forces the equilibrium violently to the left. This drastically reduces the solubility of the compound. Today, highly advanced water purification facilities use this exact trick to deliberately pull specific toxic materials right out of our drinking water. But the way we actually manage these super complex equilibria is going through a massive revolution. Welcome to the automated labs of 2026. Instead of human scientists manually tweaking knobs, we now have closed-loop systems using real-time spectroscopy to visually track equilibria. Multimodal AI instantly calculates Q on the fly and dynamically adjusts temperature and pressure. The result? Work that used to require months of rigorous trial-and-error human optimization is now being resolved perfectly in just a few hours. So the really crucial takeaway here is how this AI integration scales globally. We aren't just trying to pass chemistry exams here. These automated labs are engineering green plastics, they're optimizing clean hydrogen storage, and synthesizing highly targeted pharmaceuticals. Most incredibly, they're using precise electrical inputs to force highly unfavorable gaseous equilibria to shift toward carbon utilization. They are literally pulling greenhouse gases straight from the air and transforming them into stable, solid carbonates using single-atom catalysts. Which leaves us with a truly awe-inspiring thought. From a quiet glass of soda sitting on your desk to next-generation AI laboratories pulling carbon from the sky, dynamic equilibrium is the silent director of the entire physical world. It ensures our matter remains beautifully, perfectly balanced. So I'll leave you with this. If our very existence is dictated by this perfectly balanced microscopic war, what happens when humanity completely masters cosmic equilibrium? Stay curious and keep questioning.